have a lab next time. Lab next time. John? All right. So we've talked about heat. We've talked about heat is that energy that transfers from one object to another. But we haven't talked about how it transfers. Heat transfers by one of three ways. It's either by conduction, by convection, or by radiation. These are your chapter 22 notes. These are lecture notes. What? Yeah, it makes a convection cell on that. Conduction, convection, or radiation. One more time. All right, so conduction, transfer of heat by direct contact. Those things have to touch. They have to touch. This is how heat transfers through solids. And the rate at which conduction happens, which is what you are going to be looking at next class. You're looking at rate of conduction. Well, it depends on a couple things. One, first of all, what is the material? What is the material we're using? Not everything has the same conduction rate, being equal. What is the thickness? In other words, things that are thicker tend to conduct faster. Let's think of it as a pipe. Can I shove more water through a little skinny pipe or a really big fat pipe? Big fat pipe is going to be able to carry more water. The big fat bar can carry more energy. The length. The longer it is, the longer it takes to conduct, right? Because it has to travel a longer path. Also, the difference in temperature. The greater the difference in temperature between the two ends, the faster it's going to go. So, like your walls, wall heat will conduct through the walls, whether it's a warm inside and goes outside, or it's hot outside comes inside. How fast it goes to the walls will depend on the difference in temperature between the inside and the outside. On that. And one more time. Now, conductors. We've talked about conductors with electricity in our star review, but it kind of works the same way for heat. Transfer energy easily, and for many of the same reasons, they have weak bonds. Now, let's visualize. I have a big, long line of soccer balls, and they're all joined by springs. Now, I grab the first soccer ball. That'd be like me sticking a steel spoon into the boiling water. Okay? Comes in contact with the boiling water excites the electrons in that first soccer ball. Now, as I shake the first soccer ball, what's going to happen to the next soccer ball? It's going to start to shake. And as it starts shaking, what's going to happen to the next soccer ball? Shake. And eventually, if I shake it long enough, what's going to happen to all the soccer balls? They're all going to shake. Well, that's like you putting that steel spoon into the hot water. Because you put your steel spoon in the hot water, you come back a little later, you grab, and it's hot. Ouch. It's all really hot because the energy's gone down. Now, insulators transfer thermal energy poorly. What does that word? Poorly. Does it mean they don't transmit thermal energy? No. Strong bonds, fewer electrons. Also, does that mean it's not going to get hot? No. This would be like putting a wooden spoon into the boiling water. Now, the wooden spoon, the first one, now I have my soccer balls and I have little bars. Instead of springs, I have bars. I shake the first one. Is the next one going to move? Yeah, but very much? No. And the next one might move just a little bit, but eventually after 2 or 3 soccer balls, are they going to shake anymore? No. But the first one is shaking a lot. It's at a high temperature, right? Because although I can grab the handle of my wooden spoon, if I took it up and grabbed the part that was in the water, is the part in the water hot? Yes, it's very energized. It just didn't pass that energy along. That's an insulator. It still get hot. It's like if I heated glass in a flame, and I mixed up, like, here's some hot glass. One of these is hot, one of these is cold. Can you tell the difference between hot and cold glass? Yeah, when you touch it. But I mean, looking at it, no. I mean, so they just like hot and cold wood. You don't know the difference between hot and cold wood either. You know, that's another thing about insulators. You really can't tell whether one's hot or cold on that. Okay. So we're going to do a little thing. So we're going to do a little exercise here on this. And it takes a little bit to run, so we're going to start it off. And so I have here on this bar in counterclockwise, so I have aluminum. Now, all these bars, all the bars are the same length. They're all the same length. They're all the same diameter except for one. We'll talk about that one. So they're all the same length. They're all the same diameter. They're made out of different materials. And because we're going to heat the center, they all have the same difference in temperature. So the center is the same temperature, and the outer edge is going to be the same temperature. The only difference basically between any of them is what they're made out of. And so I want you to draw this picture in your notes on here. So we have aluminum, brass, copper. Now we have this thick iron one. We'll talk about that. So we have a thick iron one, we have a thin iron one. Nickel gold, a nickel gold alloy, and nickel. Okay. So what I want you to do is basically number these 1 through 7. What order do you think these little paper clips are going to fall off? The paper clips are held on by wax, so when the energy gets down there, the wax is going to melt and it's going to fall off. Okay, so we're using wax and paper clips are our detector. The one that gets hottest first is going to fall off first. Now, thick and thin iron. One of our things is, does a thicker bar matter? So these two bars are made out of the same material. Everything's equal except the thick one has twice the diameter of the thin one. So you also want to know which one of these two iron bars is going to conduct the fastest, the thick one or the thin one. And the thin one is just the same as all the other ones, but you have this thick one that has twice the diameter. All right, so we're going to start this up. So it's going to heat up. We'll let it keep doing its thing. We are going to do a little exercise here. Exercise. And so what I want you guys to do is, starting right here, stand up. You guys are going to stand around the room, shoulder to shoulder, going that way. You're going to see my first one. You're first. So right there. So stand sideways, shoulder to shoulder. Everybody move. Everybody. Shoulder to shoulder. You guys are my conductor. You guys are my conductor. You guys need to go there. Move, 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 move. On that. Okay, so we have our high temperature end of our conductor. Then we have our low temperature end. Jennifer, you are the end. You have that little box. And what's going to happen is our energy is going to start over here, and you guys are going to pass hand to hand down to the other end. You're going to put it back in the little green box. All right, so you can start conducting. If you drop it, let it go. Okay. Now notice, did the energy get there right instantaneously? Takes time. Takes time for it to get down. Another thing, up, first one fell off, copper. Copper was first. All right. Now, so we'll come back and talk about that. So the thing is, now we're coming down to the end. Is the energy moving through the conductor? Is the conductor moving? No. Aluminum fell off. So the thing about conduction, the energy moves, the material doesn't. It passes it through. All right. So if you bring me that green box, okay, you guys can have a seat. Thank you for being a very good conductor. You're like the first class ever not to drop one. Most touch number. Okay, so aluminum over here was number 2. Aluminum was number 2 on that. So this is conduction. All right, which brings us to convection. Convection. Okay. Now, convection. Transport of heat by mass movement of a fluid. Okay, that's basically what that means is that something is going, this fluid is going to pick up some energy, it's going to move someplace else and give up the energy. Now, how does that fluid? Now, fluids are gases and liquids. Gases and liquids are poor conductors. Perhaps just fell off. Fluids are poor conductors. They are good insulators. How does it pick up energy? Well, it does pick it up by conduction. In other words, it's kind of like that wooden spoon. That fluid touches the hot object, picks up some energy, and then moves somewhere else on that. And we can give a demonstration of that. So the Curie and Coulomb, Curie and Galileo group, please stand up. Just stand in a line that way. Stand in a line that way, facing me. Stand in a line facing me. Okay, so these guys are my conducting fluid. They are going to pick up some energy. They are going to walk around the room. They're going to put it back in the box. And they're going to continue coming around, pick up some more energy. And they are going to keep going around, delivering up my energy from this point to the other point until I tell them to stop. Pick up some energy and convect. Okay, so notice they have picked it up by conduction, right? They had to touch it. And they're hanging on to it. But now, unlike conduction, is the medium moving? Is the convecting medium moving? They're moving, right? You didn't move before, but they're moving. And so they're going to carry the energy from one place to another. All right, and then once you guys come back around, you can sit down. Now notice the shape. What's the shape? It's a big circle. They're making big circles. You guys can have a seat. Thank you. So a round of applause for our convecting fluid. So the fluid, so notice unlike conduction, which is the energy flows through, the convection you have to pick it up, you have to carry it someplace, and you put it down on that. And then it comes back, but it's a cycle. It's a cycle. It's a circle on that. Notice these little pictures. It's kind of like when you boil the water, when you make pasta. If you really look at the recipe for pasta, it says get your water to a fast boil or a roiling boil. Now, if I barely have the water boiling, or I have it boiling so much that there's bubbles coming over the sides, is it going to cook it any faster? It's going to cook your pasta any faster. A little bit of boil or a lot of boil, cook it any faster. Because the temperature of both is 100 degrees Fahrenheit, or Celsius. Both are 100 degrees Celsius, so it doesn't matter whether it's a lot or little on that. Lot or little. But there's also cooking it. There's other factors. Because if you had a little bit of boil and you pour your pasta in and it just sits on the bottom, what happens? It'll stick. But if I have that fast boil, which basically I set up this little convection cell, do I have to really stir it as much? No, because the pasta is going to be always moving around because the heat is going to cause it to come up in the middle and it goes down by the edges. And if you notice, it comes up in the middle and it goes down on the sides because it gets cooler on the sides on that. Now we do have a phenomena around here. I can add in. Oh, number 4. The big one. Big iron with number 4. So thick iron. Thick iron goes faster than thin iron. Is that what we said? That a thick bar is going to be faster than a thin bar. What we also discovered is steel, particularly a great conductor. Because these three went a lot faster. The aluminum and copper went pretty close together. Why do we make all our cookware out of why is the best cookware out of steel? What gets hot? Well, one, it's a lot more durable. It's hard to harm steel pots. Cast iron skillets last forever. They'll last forever. But also, from a health standpoint, I mean, there's health reasons. Better to cook in steel because whenever you cook something, it puts some of the pot goes into your food. Is iron bad for you? No. In fact, most of us, do we get enough iron? A lot of us get enough iron in our diet? No. Most of us don't get enough iron. What part of your body needs iron? Blood. Blood production. A lot of people don't get enough iron, especially girls. Teenage girls don't get enough iron in their diet. All right, so it's one of those things. Like guys too, we don't get. Your age needs it more than people my age. Things like that. But iron is one of those things. Aluminum. They made a lot of aluminum pots. After World War II, aluminum, they thought, okay, this is a miracle thing. We're going to make all these white pots, and it's great. But they have found, I know I've read some articles that suggest that, in other words, when the people with Alzheimer's, when they do autopsies, and they do that, they find a lot more higher levels of aluminum in their systems. So aluminum might be that. That's not to say a lot of steel cookware. Like my cookware at home, we have a big aluminum thing melted on the bottom of the pot. Why? It's a heat sink. It helps that pot and things like that. So we use for other things. Yes, sir. Well, probably because it's thin, it cools up. Well, aluminum. It's probably aluminum because it's in the air. It's thin. It's that whole sparkler thing. It's very thin. Whereas the tray itself is a lot thicker. Going to give up its heat slower. Although aluminum has one of the highest specific heats for metals. So it actually takes more energy to heat up and cool down aluminum. It's like, okay, so we got the other one that almost never comes up. I've never grabbed long enough to keep that one going. But we can see that the nickel and aluminum. So this is number 5. Number 6. 7 obviously is the straight nickel. Nickel is not a great conductor of heat on that. So write a little summary of what you wrote about that, about conduction, but we can see different materials are going to conduct. There are better conductors on that. Right, just a little bit about that. Now, term you hear a lot in the Bay Area about our weather is called microclimates. For different places in the Bay Area, a lot of different microclimates. It changes a lot. I grew up in Marin. In Marin, generally, it's about 10 degrees colder in the winter and 10 degrees hotter in the summer. It is here. It also rains a lot more in Marin than it does here. It's mountains and things like that. But and that's about 50 miles north, where I grew up. So we get in, but there's one thing that's why one of the reasons why people like to live here, because we have our own air conditioning. Our own air conditioning. It's one of the reasons you don't find too many houses with air conditioners around here. Now, so we have Pacific Ocean, San Francisco, Sacramento. And in the spring and in the summer, in the evening, a lot of evenings, afternoons, what starts to happen? On about 4 o'clock or so. Well, why does it get cooler? The wind starts to blow, doesn't it? Why does it blow in the afternoon like that? Well, it's one of these microclimates. Well, let's think. Sacramento. Sun comes up. Morning. You have air getting its sun's energy and getting warmer. The ground. Which gets warmer faster, the ground or the air? The ground. So the ground has a higher temperature than the air, so any air in contact with the ground is going to gain energy. If it gains energy, it gets more energetic. It expands, and if you expand, what happens when air expands? It does what? Goes up. So you have rising warm air. You have rising air over here. Over the ocean. Well, does the ocean ever warm up, really, day to day? No. It is the same temperature. Does the air warm up? Well, yeah, it gets warmer than the ocean, so the air starts losing energy for the ocean. Well, if warm air goes up, cold air must go down. So you have, we call that sinking. So we have sinking cool air. So now you have all this air piling up down here. It's piling up, it's piling up, it's piling up. What's going to happen to the air pressure? Go up or go down? Go up. Higher pressure. This is all going away. We're losing air, losing air, losing air. The pressure is going to go down. So we have a lower pressure. What causes wind? A difference in air pressure. Is this the only way this happens? No. There are lots of ways that you get this air pressure difference. There's lots of ways this happens. This is one way. Okay, this is one way, not the only way, but this is what happens here. Okay, so we get this lower pressure, so what happens is this high pressure air starts to move that way. And we call moving air wind. Okay, and this forms what's called a sea breeze. Why? Because it comes from the sea. Yeah, wind is named where it comes from, not where it goes to. A west, if you say, oh, we have a westerly wind, that means a wind that comes out of the west and is going toward the east. Going toward the east. So we have that. Well, conversely, so we have this cool air. Remember, this is cool air. We have warm air going that way. And notice we are forming a convection cell. Just like our convecting fluid in here goes around a circle, we have a circle. So what happens? We have this cool air coming off the ocean. It goes across the valley floor. It picks up heat energy. It picks up all that heat energy. Well, if the energy is going from here into there, the land is getting cooler. And it gets to the Central Valley, and it heats up, and it rises, and it carries this warm air, and all that energy ends up where? In the ocean. It cools down again. And it keeps doing that. And so this forms in the evening. This is our air conditioner. Because when these winds do not appear in the summer, what happens to us here? It gets really, really hot. Basically what happens is you get a high pressure over the Central Valley for other reasons. It's really big high pressure. This wind does not form, the cell does not form, and it gets really, really hot. When the high finally breaks up is when you see, when it starts happening, you see the fog up on the hills, and you know, oh, it's going to cool off tonight. You see that fog, you get that fog up on the hills, you know it's going to get cooled off that night. That sort of thing. Forms convection cell. Now this is what happens during the day. So it'll keep blowing until sometime after the sun goes down. Now the sun goes down, the air and the ground start to cool off and things like that. Now, nighttime. Cooled off. Ground cools off faster than the air. So now it has a lower temperature. So sometime in the early morning, 2 a.m. or something, it now has a lower temperature than the air. The air starts to lose energy to the ground. sinks. Over the ocean, the air is cooled off, it is now cooler than the ocean water. It starts to gain energy from the ocean a little bit. It starts to rise, and again you get this higher pressure, lower pressure, and so now you get it going this way, and we get what's called the land breeze. You know, so if you get up about 3 or 4 in the morning, you feel this very gentle breeze in the morning. Now, if you wait till the sun comes up, it's not going to be there, because basically it stops within literally minutes of the sun coming up. And it heats up in the Central Valley. It stops really quick. But this land breeze is much, much less than the sea breeze. Why would the land breeze be less than the sea breeze? What is the major difference between night and day as far as this wind is concerned? It's not as much as calmer. Let's think about the two locations, Ocean and Sacramento. What is different about those two locations at night than they are during the day? What about temperature? During the day, there's a greater difference in temperature, right, than at night. Night, it's not very far apart. You have a potential freeze. The greater the temperature difference, the stronger the wind. So that's why the sea breeze is much greater, because there's a much greater temperature difference. You get and because of that difference, you get a lower pressure, higher pressure sort of thing out here. All right, questions? Video.
Eureka! The story so far. Objects immersed in a liquid are buoyed up by a force equal to the weight of the liquid displaced. This is called the principle of buoyancy. If the object has the same density as the liquid, it will float in the middle of that liquid. If it is more dense, it will sink to the bottom. If it is less dense, it will rise to the surface. And now, convection. You look nice and warm. Where does the heat for that hot water radiator come from? The furnace, of course. In the basement. Where is the furnace always kept in the basement? Why couldn't it be in the attic for a change? What would happen if it were? Anyone on the floor below would freeze. That's what would happen. Why is this? Well, let's put the furnace back where it belongs so that we can see how a hot water heating system works. The furnace heats the water in a tank. The hot water rises up through these pipes and into the radiators, where it cools, and then the cold water flows down through these pipes and back into the tank, where it is heated up again, and so on. But why does hot water go up and cold water go down? Because of the principle of buoyancy. If you hold something that is less dense than water, such as a cork, in the middle of a beaker of water, the buoyant force pushing that cork up will be greater than the force of gravity pulling it down. And as soon as you take your hand away, the cork will rise to the surface. Now, when water is heated, its molecules speed up and it expands and becomes less dense. And this less dense water will therefore go up, and then cool and become dense again, and therefore go down. And that's exactly how hot water heating systems work, and why your furnace is in the basement. But the house next door hasn't got a hot water heating system. It's heated by means of hot air. And yet, your neighbor's furnace is also in the basement. Why? Because the principle of buoyancy applies as much to gases as it does to liquids. When air is heated, its molecules speed up, and it expands, and becomes less dense. And so hot air rises, just as hot water rises. That's how hot air balloons work. When the air inside the balloon is heated up, it expands. And therefore there's not enough room for all of it inside the balloon, so some of this hot air escapes. The result of this is to leave fewer air molecules in the balloon than before. In other words, the air inside is now less dense than the air outside. So the balloon floats upwards, just like the cork from the beaker of water. The fact that hot air rises also comes in useful when cooking a hot dog. It'll take forever to get hot if you hold it beneath the fire. But if you hold it just above the hot air which is rising up from the fire, you're in business. And this is why your neighbor's hot air heating system is able to work on the same principle as your hot water heating system. Hot air goes up, it cools, and the cold air goes down. Since the behavior of gases and liquids is so similar in this and many other respects, and since both gases and liquids flow, scientists refer to both as fluids, and to the type of heat transfer which carries or conveys hot fluids upwards and cold fluids downwards as convection. And it's thanks to convection that balloons go up, hot dogs get hot when you hold them over a fire, and one furnace in your basement is enough to heat your whole house.